So Sven is from LMU Munich, and he will tell us about learning, symmetries, and integrability of physical systems with AI. Please go ahead, Sven.
Let myself unmute myself, otherwise this could be funny. Okay, yeah. Thanks a lot for the organizers for putting together this very nice workshop. Hopefully at some point we can actually all go to China and have the seminar, the symposium in person. So today, as Fabian said, I will talk about symmetries and integrability of physical systems and finding them with AI. But let's start very general, why we kind of start or got interested into this whole subject. And that's really these remarkable results that come in various domains. I'm picking one because it has had nice media attention and was kind of personally very interesting, namely that of AlphaGo, when we've seen the beating the world champion. And particularly one thing I was very much amazed by was to see that AlphaGo was using moves that experts kind of discarded over centuries. And that's something, I think is very interesting, because this naturally kind of brings up a very interesting question, namely what would be similar type of discoveries in physics done by machine learning that we as physicists have missed over the centuries. And so what is this talk about? Well, let me start with what this talk is not about. So we've seen in machine learning, it's by now quite common to kind of go, try to obviously get more insights out of your data, out of your simulation, understand it more, and you can apply this in various frameworks. And one key aspect to the success of this is to actually imply domain knowledge, or respectively, if you want to call it bias, into the machine learning framework. So this is, for instance, to say how to incorporate your symmetries in your network. And the whole unifying picture of this is geometric deep learning. Now, this talk is about when you don't know about this domain knowledge and the question of whether you can extract this domain knowledge and these biases with machine learning. So for instance, if you're interested in the question of finding out what are the symmetries of a system. So to get started, let's first of all recap why domain knowledge is very much key and why this has been a continuous success story in the rise of deep learning. And that is basically that by biasing our neural networks, we are able to overcome the standard curse of dimensionality that we have faced, which wouldn't allow us to get good neural networks with just to classify images and also to learn about molecules, etc. However, if we apply domain knowledge, so for instance, particularly in the context of image classification, something simple as translation invariance, successes arise. And this is here kind of this ImageNet success story in 2012, which kind of started. And since then, obviously, has been applied across various domains. And we see this also when we apply this in physics and mathematics. So for instance, if we are looking at getting numerical Calabi-Yau metrics, so I guess Fabian will talk about our work later, then we see that making the right ansatz for the metric is actually very helpful. Yeah, so that's kind of, if you don't know about it, then the ansatz, then it is hard. And so, but there's naturally, obviously, another question is, what do we do in situations when we do not have domain knowledge? And can we use AI to identify this correct domain knowledge? And the overall question then is really, are we missing kind of organizing principle, organizing structures in our data, and can we find them? If we step back to see, to put this a bit into context, with discovering such structures. If you think about chemistry, for instance, pre-1869, this would be discovering organizing principles like the periodic table. And indeed, this is something you can ask a computer to rediscover, and this can be done. In terms of particle physics, similar questions could be phrased in terms of, refining standard model of particle physics, or Gell-Mann's 8-fold way. But what I want to ask is, what do we know? Which kind of tools do we need to make such discoveries in the 2020s? And there, for me, there's a repetitive pattern, is to identify the mathematical structures to describe an efficient a system more efficiently. And this can be put across various domains, and which makes this obviously very interesting, very widely applicable. So this you can talk about this in the context of astrophysics. You can talk about this about studying strongly coupled systems, and you can talk about this in the context of Calabi-Yau manifolds of string theory. Short, what we're interested in is finding developing technology that allows us to find the underlying symmetries, dualities of our system. And when we are done with that, then potentially also implement it, deploy these kind of structures automatically in our ML pipeline. So let's get started. Put this into this whole picture into concrete information. And this starts with finding symmetries. And this is work which the PhD student here in Munich, Mark Sivery, and where we're looking for symmetries from deep kind of representations the neural network is adapting. So what's the problem here? What do we want to search for? So let's pick a very simple toy example to understand what we mean with actually finding an underlying symmetry. So we consider here the standard Higgs potential, and this has clearly a rotational invariance, and we can obviously reduce this in this radial representation here. And the question is, obviously, how can we find this kind of invariance? And then once we've identified this invariance, what symmetry is behind such an invariance? How can we do this? We need to have a method which groups the input together, which has the same meaning. And in terms of the Higgs potential, this means that we would like to group these points together, these types of points together, and these types of points together, but not these and from these different classes, from these different representations in the same place. And how we want to do this is by looking at the embedding a feed-forward neural network is taking very deep in during the network. So down here, when it's performing a very simple task, namely a classification task. And it's obviously something which has appeared before, and this is known as word-to-vector. And so what this means is that if you're doing some language classification, is that when you're looking at the embedding of these words in these, then words of the same meaning are roughly put to the same position. So if you're looking at the difference, for instance, of England minus London in this embedding space, this equals then the distance of Paris minus France. And so what we want to ask is, can we search for symmetries in this way? And the answer to this question is affirmative. And so we look at various examples in the paper. So let me show you how this embedding layer looks like. So what I'm showing you here is a dimensional reduction of this high dimensional space by using a stochastic neighbor embedding, SNE, and I can visualize where these classes are lying. And what we see is really that these classes are being separated and things of different meaning are pushed aside. Now, when we have this, the next question is then, okay, how can we go about when how can we determine the symmetry? So we are effectively left with a situation where we have connected points in input space. So something like this, such a point cloud. And we want to know which symmetry is behind this. And basically what we do is we determine the generator connecting these points in the subspace. Essentially, you can look at the nearest neighbors and you can see what is the common, or what are the generators connecting. You can do this procedure a lot of times and see what is the most dominant component. And when you look at it, it is actually your standard SO2 generator. You can do the same thing for other symmetries. You can do this for SO4, SU2, or SO3. And this works for a reasonable amount of points. Now, that's the first kind of aspect to the story of finding symmetries. Now, then we went on to actually go a bit further about having a different procedure of finding symmetries from data. And this is by just basically looking at samples of phase space and automatically finding them for that. Let me present you a little bit of background to this story. This goes back to work by Battaglia et al. In 2016, when we're facing the following problem, namely that we're interested in finding the dynamics from just some images. And basically you want to see what are the next moves. So you want to predict it, you want to learn the underlying dynamical model. What we will focus on in this talk is basically a sub-problem of this. Basically, you're given just the momenta and the positions of the particles, and you want to predict the next steps. Now, again, you can try to do this with a standard feed-forward neural network. And here I'm showing you results for a two-body system in a gravitational potential. And you see that this works kind of all right, but not really good. And again, the whole story repeats itself, that we need to know what is a good bias for our network to learn. And what it turns out, this is work by Krippendorf et al. What is a good bias is to use your physical knowledge and basically enforce that energy is being conserved of this system. And how do you do this? Well, you basically, your network predicts the Hamiltonian, and then you're taking, predicting P dot and Q dot by taking the derivatives of this output function with respect to P and Q. Now, what we then wanted to ask, and these results were actually then shown here, you see the difference, and this actually, improves upon the results. Now, what we wanted to ask is, can we learn more structures from the samples of phase space? And in particular, can we learn it, can we learn the symmetries of the system? And again, we can do this. And let me tell you how this works. So what we do is we look at, we're looking at doing an appropriate coordinate transformation, learning a coordinate transformation. And then what this coordinate transformation does, it singles out the cyclic coordinates of the system. So this is really key. We know that for conserved quantities, Poisson bracket of the Hamiltonian with this cyclic coordinate vanishes. So now, how do we implement this? Well, again, this has two key steps. We know what the loss is that we want to implement, namely based on that Poisson bracket. And so we formulate our problem as an optimization problem, and then we obviously have to train and make sure that this is learned. Now, here's the setup. So instead of looking at this Hamiltonian neural network kind of setup, what we do first is we have two networks, which the first one is learning essentially a different coordinate representation. And the second one is then taking some of these as input and learning the Hamiltonian of the system. Now, you have additional constraints, basically, modify your loss functions. And what this does, it ensures that you're not just using energy conservation, but it enforces additional constraints on the motion. So it basically ensures that your motion is taking place on the hypersurface in phase space. Now here are some results of some sample trajectory, and you can see that we get this can get this to work. Well, you have to go through a little bit of algebra, formulate these properly as loss functions, and then you can also, compare the trajectories, not just on a single level, but on general, how well generalization is working. In fact, as shown here, we see that our trajectories are far superior to, or are superior to Hamiltonian neural network trajectories. Baseline trajectories are completely out of the window there. And you can ask how much, other quantities conserved, which are not necessarily enforced by Hamiltonian neural networks, such as angular momentum in this case. Now, in addition, and that's, I think, coming from physics, which is very interesting, is you can ask what are the quantities that the network is singling out here as coordinates, yeah? And vice versa, also what kind of Hamiltonian it is actually learning. And so, here in simple examples, you can just simply fit some polynomials to it. And nevertheless, I think it's a non-trivial exercise because a priori, you wouldn't have no clue. You don't know whether the network is actually picking up that angular momentum is conserved. In this case, nevertheless, you see that it is, picking this up as a constraint. And like really, as a connection, as the one is to learn these constraints, but also they're potentially, if we're thinking about, all sorts of constraints we have, they potentially go beyond normal geometric consistency conditions that we can find. And so that's, I think, it's a very interesting direction. Now, in the remaining part, let me talk about, pushing this kind of line of thought a little bit further. And that goes to work which appeared earlier this year, together with Dieter Lüss and Mark Silvery, where we are pushing the symmetry idea further in order to also search for whether a system actually can be seen as integrable. And so this goes back to a speaker which was speaking earlier in this conference, who asked us at some of these, physics ML meetings, whether, that learning these symmetries is quite nice, but, what happens if you can, face situations where you have infinite number of symmetries, as you have in some integrable systems. And that's clearly a very interesting question. And I'm happy to report that this can also be addressed. And so let me give you a lightning review on integrability here. For those of you who are not working in this field, is basically we've seen this additional constraint on motion that is appearing with conserved quantities, and the system is called integrable if and only if there are n independent, everywhere differentiable integrals of motion which are in involution. And there is an alternative way to look for this, is basically to look for a different representation of the system looking for such a Lux pair. And in this language, the conserved quantities are given as taking the power of this L matrix to the power k and taking the trace of it. As an additional condition, you have to look that they're in involution. Putting this into a simple language of a harmonic oscillator with the standard equations of motion, then the Lux pair can be written as such, and you can check what the associated conserved quantities are here, it's kind of trivial. Good. One additional important constraint on this whole business is that these, if you were to take just, for instance, to be 0 identically, this would identically be satisfied, but the condition here is important, namely that these matrices have to be non-trivial in such a way that the equations of motions are satisfied. Okay, now let's put this into, why is this interesting? Why is this challenging? And to kind of highlight this, I'm just, copying here basically statements that are made, by Nicholas Bicert, one of the, very people very much involved in integrability and having pushed this field very much further. And he's describing, having a lax pair formulation, is very convenient, but it's by no means clear how to find it. And this is the kind of thing, that obviously humans do over time come up with, but it will be, much simpler to search for this just simply with the machine. Clearly, integrability is a huge important thing because, knowing about these symmetries can simplify the system very dramatically, and this has implications not just in classical mechanics or classical field theories, but clearly drives into spin chain models and wonderful stories in the context of n equals to 4 solved by Yang-Mills theory, which we're obviously, not talking about now. But finding this lax pair and this lax connection, how can we do this? Yeah, with machine learning. And again, the story is the same in the sense that we want to formulate the whole problem as a, as an optimization problem. And what we want to do is, obviously, we want to do this without knowing what the lax pair is. So the only thing that we can do is, or what we use as data, are samples from this phase space. Once we have the Hamiltonian, we can easily write that, get those samples. And so how do we formulate this optimization? So the first thing is obviously to ensure that the lax equation is satisfied, so you can formulate this as a loss. But then things become a little bit more involved and more tricky in the sense that you also have to ensure the equivalence to the equations of motion. And this can be done as follows, namely that you can look at the following thing. Namely, if you're looking at the equations of motion, usually they simplify or can be written in a slightly simpler way, namely in such a form. And this tells you something because it tells you that L has to include the xi's in some component. And put alternatively, L, the commutator of L and M, has to include these fi's. And this, has to include it means that it has to be proportional to it in some component, and that you can formulate as a loss function. Again, like as there are some experts here on the Calabi-Yau metric story, so this is very much similar in some sense of balancing two things that are very proportional. So if you're thinking about the sigma loss, it's very much similar to the loss functions that we are placing here, and we are formulating here. And then this is not enough, and we need to kind of make sure that our networks really are forced not to collapse to 0. Yeah, really pushing them hard away from 0, and we add an additional mode collapse loss. So in total, we have these loss components that we use. Now, in terms of our networks, so we start with a very physics-inspired setup, namely make things simple. If you start with something which looks like this, we just take some coefficient you're fitting, it actually is too simple in the sense that your network has too few components, and you convert most of the cases. Really depends a lot on the initialization. So to make it a bit more flexible, we add a little bit more flexibility, and better shown here as a summary. And it's single individual components. This kind of softmax is basically adds more parameters to the whole procedure. Now let me show results here. So here, this is again for the harmonic oscillator. So you can run this business. You can look at samples from phase space, and you can run this this procedure, and you get out the Lux pair, and you get out, and you can then check, obviously, whether these conditions are, how well they are satisfied, and you can also check what the conserved quantities are. In this case, it is it's very much matching towards what you are expecting. Now then, we obviously went on to go to more sophisticated system. So let me show a couple of examples here. So this is a so-called KDV system. So this is basically looking at waves in shallow water, governed by this equation. Here, this is a field theory example. So you're not faced with a Lux pair, but you have to go to make it local. You have to go to a so-called Lux connection. Still, the procedure follows through, and you can refine the connections that are known in the literature. Going to simple Heisenberg magnet, we're going to standard example of nonlinear sigma models, in particular, Sine-Gordon equation and the principal chiral model. Again, this works through. Now, let me mention as a last kind of example here, another very interesting application. So often you're faced with a situation where you know that a certain system is integrable, but now you're asking, okay, if I add a perturbation to it, if I add a perturbation to this, the perturbation. If I add a perturbation to this, then the question is, does the system remain integrable or not? And in particular, this is really, if you want to go through, how can you deform your system in order to still remain integrable? Now, this is something which, we can start to address here. And let me show you a couple of results. So what we can do is we can initialize our network at a known solution for the unperturbed system. So if you know what a Lux pair is, and see how it reacts to samples from a perturbed system. And this is what I'm showing you here. And you can see that for an integrable perturbation, it really can relax to in this case, to this. Whereas non-integrable perturbations, it really struggles with it, and it can really see quantitatively a difference in how it is performing. Now, here's obviously, this is not, if you see some perturbation to be, not converging, this is not necessarily saying that this is non-integrable. It's just saying that, your Lux pair, your network is not sufficient to do that. However, it's, can be used here as a discovery tool in the sense that you can check that a perturbation is integrable. So in the sense that, if you see something positive like this, then we say this shows an integrable perturbation.
You have 5 more minutes, Sven.
Okay, good. I'm actually doing good on time. Thanks. So yeah, let me conclude and give a bit of outlook, and then we have plenty of time for questions. And I'm happy to explain things much more in detail as well. So what I've shown to you is basically a way or various ways of extracting domain knowledge with machine learning. And so the first example where we for symmetries was from looking at the embedding layer. So we were looking at relatively deep, several hidden layers, and then look what the embedding that the neural network is taking on a simple classification task. And that really, gave us a clue about what symmetries are there. The other thing that I've talked about, where actually, physics bias plays an important role, is in looking at simulations. So in particular here in the context of very simple systems, obviously, but to get very accurate results just from these samples, it made sense to not use just a simple neural network, but to turn on your physicist's hat and come up with a network that incorporates certain features you definitely want to have, such as energy conservation. And then subsequently, what we showed is that it also helps to enforce the symmetries. And so this does two things at the same time, obviously. This not just only finds the symmetries, but it also uses them. And that's, I think, is very, very interesting. And this whole kind of story that, also underlies the integrability part is basically this whole story is possible when we know what a loss function is. Yeah, when we can formulate a loss function that kind of shows this procedure. That's important. As soon as you can do this, you can tweak your machine learning ansatz and see that you find something that is convergent. Now, then in the final part of the talk, I use this to actually go a step further and to look for Lux pairs and Lux connection. Here, just clearly case for classical systems, but nevertheless, I think very interesting. The only thing we need really as data is just looking at samples of phase space. And as an interesting application is obviously that you can look at perturbations and of these systems and see whether they are integrable or not. And with that, I would like to thank you for listening. And in case you're interested for these kind of talks, I would like to advertise to you this seminar series, this online seminar series we are organizing, Physics Meets ML. Please feel free to go to the website, look for talks, look on our YouTube channel to see past talks. And yeah, with that, I'm happy to hear your questions. Thank you.
All right, thank you very much, Sven, for the very nice talk. Yeah, you were right on time, so we actually have time for questions. Are there any?
So I have a question. This is George Mays. Sven, that was a wonderful talk, really very illuminating. A very simple question I have regarding actually your harmonic system. So suppose that you have an inverted pendulum, and we know that we have an inverted pendulum, right? And if we drive it, right, with some force, with some frequency, then of course we can have regular periodic motion. And I think we do that in our mechanics classes. But then we also point out that depending on the frequency, we can have a transition from periodic motion to chaos. It's a very simple system, right? It's almost like a paradigm of chaos. So would the AI system, would the machine learning algorithm discover this possibility? A more complicated thing would be, you teach the system to do a two-body gravitational physics, then you introduce the third body. You're going to introduce this perturbatively. Maybe the system will find the Euler solution, the Lagrange solution, blah, blah, blah. But we know generically it's chaotic. And so how would the machine learning algorithm approach this? Have you thought about that?
Yeah, it's a very interesting question. So yeah, let me comment a little bit. So I think so for the chaotic example, this actually touches upon a very interesting point, right? Because like what we train it with is points from phase space. So if you take it from the, points of phase space, which are inside the regular regime, the AI system would always think, okay, it can only predict regular systems. It would only learn this system, right? It would generalize although I haven't tested this, I would be almost certain that it will be very badly predicting things if you go into the chaotic regime. In the system. So it really depends on what you say. I mean, you can turn it around, because that's a very interesting aspect, that you can, say, feed the system just subsystem, sample sub-regions of phase space to see whether structures still are there. Good. Now, but this is, in fact, I think, so another interesting aspect to that story is then, okay, is actually to study this explicitly, yeah, how it behaves on, when you go slowly towards this, when does it stop converging, etc.
Yeah.
So I can say you a little bit. So for instance, I'm showing you here a 2-body because it's, converging really nicely. If you go to a 3-body in a very simple approximation, right, things become harder. Yeah, in fact, for predicting this. Now you can get around this if you do more sophisticated things, in the sense of, instead of looking at the standard feed-forward network, looking at the graph kind of language of graph neural networks. But yeah, so again, I think, yeah, the ways of, approaching those, and I think, that's super interesting, yeah,
okay, thanks.
Yeah.
Very nice.
I have a question.
Yes,
I
please
don't
go.
know, it might not be very well formulated, but I'll still try. So when you gave us an example of Go, a machine learning thing, it is a perfect example of a first order logic system. So you give it all the rules, and machine is free to operate within those rules. Would it be correct to say, because I believe it would be correct, but correct me if I'm wrong, that machine learning can only allow you to do things, operate only within the realms of first order logic? When, for example, you told us that machine learning would be able to come up with a standard model, I do believe here it's not entirely correct, because there was the move from first order to higher order when you decided to redefine the particle from elementary to composite. And machine would be able to find you some symmetries, which you missed because there was so much stuff there. But it cannot fundamentally make the move beyond first order logic. Let me know.
Okay, so I'm not a logician. So maybe can you tell me a little bit about what's a practical way of saying, because then I can comment. I have something to say, but what's the important bit about first order logic in this context?
You have a set of axioms, and you can only operate within the set of axioms. You cannot say, for example, I give you, like for the standard model example, that's how I see it. You say, dear machine, here is the list of rules or like things. There are elementary particles. Those there is a thing, particle. Here is the rules operating on the particle. And machine can, operate on it, can find you symmetries, which you potentially missed. But it can't come back to you and say, hey, by the way, I decided that the term particle is not exactly, I don't like the term particle. I want to make it from elementary to composite.
Okay, good. Yeah, let me comment on this, because I think this is a very interesting question. Yeah, and I'm not sure I can, completely answer and completely see where this is going. But every single bit of the standard model, yeah, I could ask, you say, okay, you agree on this, say I can find the symmetry, say, and the underlying this whole story. Now you're kind of alluding at, okay, can it come up with the concept of a particle, for instance, in this context? And you would say no, I guess. But now then there's very interesting work in the sense of object detection. Yeah, so if you're asking about unsupervised object detection, you would say, okay, yeah, there's a, if you're thinking, okay, you're labeling things, yeah, and say, okay, learn this, yeah, and then it can predict that, then you effectively have given it. Yeah? But in fact, you can actually train it without giving it these labels. The way this is working, for instance, is by training this on YouTube videos, playing them backwards and forwards, so that you know where things end up at the same place. And that way, it can identify where objects are in a very nice way. So this is I can post a link for this work later in the chat. But so I would not say that it's one has to be examined very carefully, yeah, at which level we say, okay, there's a hard cut what machine learning cannot do. Yeah, if you pose it as a challenge to see the concept or find the concept of particles, yeah, I'm sure we can come up with a way of imposing, of it.
I agree, but I think the main point was that you already, as the human who programming this, making this work, need to think what are the fair questions. And unless you come up with saying, well, concept of particle is a fair game, go get, go at it. Try to find me some other concept of particle. Unless you thought about this, machine will not. So I think in this sense, machine learning is extremely useful, but it's not, it can find complex structures within the thing you already thought about. I don't know if this makes sense. So you need to think about this first before you tell machine to go try find something. Anyway, I just feel like there is a bit of oversell on the, I'm not meaning you, because you gave one wonderful talk just talking about symmetries and all the fair thing, but I guess the general what goes all around will make machine, predict new laws of physics unless you already thought about them and thought, I just don't know what the shape they take. A machine can't do this for you.
Yes, but I think so. In this sense, I think one has to be, it's a semantic. It's in some sense, right? What will you call a new law of physics? Yeah, that it's finding. I mean, at some point, it will be some descriptive. This obviously describable by some effective field theory. We've come up with the concept of effective field theories. So in that sense, this whole framework captures a lot of things. But I think the space of this is just so huge. I mean, that's a big, that's the problem that machines can help with. I think that's the.
Yes, thank you very much. That really helps. Thank you.
Yeah, thanks a lot.
If I may comment on Lena's excellent question. I mean, this is a wonderful question, but I think it's probably too deep for a short discussion. And I don't know if anyone knows the answer, but I think what she's saying in essence is, suppose you're in the 60s and you give all these properties of particles, and then, can you guess the quarks? And from the history of science, we know what happened, right? And of course, history of science is, how should I say, it's not mathematics, it's not machine learning or something, it's arbitrary, it's influenced by all sorts of things and so forth. There were seven mesons. So people, as you know, took the structure of G2 because there's 7 in G2, right? And as you know, the Japanese group of Sakata et al., they had this U3 star where they wanted to construct everything out of lambda, proton, and neutron, because those are the observed particles, and they already knew about strangeness. Now, someone comes in and says, I'm not going to go for G2 because it's exceptional. I'll go for unitary SU3. I'll predict that there is the 8th meson. And moreover, in 4 years from that time, even though everyone, when they look at SU3, said, well, you're crazy. Famous physicists said, well, this is crazy. How can it be a symmetry when the masses are so different? You cannot put same things, right, in a multiplet if they have different masses. People like Yang and others, they didn't believe in this, okay? And then someone comes in 4 years and says like, oh, and by the way, let's look at the fundamental, the 3 and 3 bar, and introduce particles which now have fractional charges. You see, it defies the logic of the time. Then someone said to say, well, you're violating statistics. Not only just the integrability of charge, how can you have 3 quarks? So then someone has to invent parastatistics or realize there's color. There are layers and layers to this discovery, right? That ultimately led to, you know, people, Gelman and Nambu, writing the QCD Lagrangian, right? And actually Nambu didn't get it right. He had integer charges. You know, it was hard to say that they are fractional charges. But then the experiments come in. You can actually see where the fractional charges come in, et cetera, et cetera. So I think if you were to give machines that situation from 1959, okay, I don't know if the machines would go for G2 as opposed to SU3, and then find that they're quarks, as a matter of fact, even though they defy the logic of the current physics, that the charges should be integral. You see what I'm saying? I mean, that's presumably has to do with this first order logic.
Yeah, but I think this is, I mean, you suggest
so
like, I'm a practical person. So in some sense, I think you can set up experiments and the numerical experiments exactly with this setup where you're actually giving it, so, you know, a subset of the data, which actually defies such setups, yeah? And you can see, okay, which solution, you know, given, you know, system you, I mean, these are, you know, wonderful, you know, experiments, and I think one should, you know, see.
No, I agree, but it's a fascinating question. I think it's the right question.
I agree with George. I think to set this up, you need to make it. Yeah, yes, you can make fractional charges. Yes, you can go at any group you like. Yes, you know, if there is not enough particles, predict another. And unless you can think of all of this, it's not going to work.
Yeah. Anyway, it's a fascinating thing to think about.
So in the interest of time, I think we have to stop here, and thanks Sven and everybody else from the session for their wonderful talks and contributions. And this ends today, so I think maybe we can continue this discussion, or maybe Yang wants to say something more. Otherwise, we'll all reconvene tomorrow for the special lecture.
You know, I just like to say that that kind of dialogue was exactly what I was hoping for. This kind of energized dialogue. So thank you for all the participants, and thank you, Fabi, and Pierre for chairing the sessions today. And hope to continue. And we've got plenty more. We're only 3 out of 14 days. So many more conversations.
Okay, so now that we stopped officially, can I make one comment to Lena and George? So I think that, so as Sven was pointing out, the machine is learning under the hood some representation of data. And for example, it learned that London minus Paris is the same as France minus whatever, you know what. But so in order to interpret that it actually learned this, you need to know that sort of you can only interpret it if you have a meaning of, if you attach a semantic meaning to this. So I think it becomes a little bit philosophical, asking whether the machine learned something which you haven't thought of because you couldn't necessarily detect it. So the machine might choose some data representation which is something deep or something trivial or something that just happened to converge to. But answering whether or not it did this requires you asking the machine a question of sort of, is the embedding such that it learns semantics between capitals and states, for example.
Yeah.
And so, Lena, if you think one could make a statement about machines never learning something beyond this first order logical, so I think this would be extremely interesting. If one could sort of answer this question using a framework of machine learning and a set of rules, sort of saying, okay, so this is sort of, I don't know, a neural network is just a parameterization of the map, and the sort of the loss landscape is what it is, and it is found by stochastic gradient descent. And I put in a specific loss function, and then I can prove that you can never go beyond this first order logic question.
But I would imagine that our colleagues in logic and computer science have asked this question, because this is you first start propositional logic, if I remember correctly, my logic classes, and then you have this first order, which is individuals, and then you have the second order with quantifiers and properties, and then you have blah, 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 and then you have this type theory. So this is this whole foundation of mathematics type of thing. that computer scientists and logicians, of course, know extremely well. So somehow you would have to, apart from the individuals, introduce these properties. And then, you know, I mean, I don't know, that's a fascinating question, but I would imagine that someone like in logic community would ask that question.
My plan was to go to Ivy Wittgenstein on the other side of the slope.
All right, there you go. You're at the right place.
I just thought I'll just drop by and see if he's around.
Exactly. I mean, just ask someone, because I would imagine they would. And this was the whole thing about this, you know, if you think of a little bit what I know from the history of mathematics, foundation mathematics, when people started thinking, right, about the foundations, do you need to introduce an extra level? And then you have to go to the meta levels. I think from what I remember of Gödel's theorem and so forth, you have to introduce a meta level because you have to introduce self-referential statements, right? That's, if I remember my Gödel, Escherbach, and Douglas.
I wish.
Yeah, you have to do this self-referential. So you have to introduce some type of parameterization of logical statement. That was what Gödel did, right, in arithmetic. And then you have to introduce a meta language that talks about that. And then you make self-referential statements, etc. Anyway, Yang, you wanted to say something.
No, I just say no. It's a pity that Boris Zilber is not at this session. I mean, he logged in this morning, but I think he's got stuff to do. I mean, it's not. But he is speaking next week. Sorry, next week. Yeah, I would love to hear his opinion. I chat with him sometime. He's a celebrated logician, so he will give very good insight on this. Maybe we'll catch him later.
And then there's this statement that maybe Fabian was referring to. You know, if I remember Penrose in Shadows of the Mind of Emperor, he has this wonderful way of presenting Gödel's theorem, and then he ties this to computability. And then he says, like, this is his non-trivial statement that somehow there are non-computable things in mathematics, and he wants to relate this to creativity. I mean, in other words, coming up with the concept of quark, let's say, or whatever, right? Relativity, or, you know, Schrödinger equation, creativity. And so I don't know. I mean, if this is true, because of course, as you know, there was a huge argument between him and logicians and AI people. But I think it drives into that direction, right? Yeah, what is computable, what is not computable, blah, 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 right? Do you need this extra layer? Something is a classical computer. Maybe you have to go to the quantum computer, blah, 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 etc. But it's fascinating.
On a very basic, it's super fascinating. On a very basic level, like one thing that fascinated me always was when AlphaGo 0 came out, and starting from complete self-play, just from random play, you know, to, you know, get to whatever performance, yeah, that's superhuman level. I mean, that's something, you know, I'm obviously saying, okay, you should win the game, but, you know, there's more to it, I think, yeah, there's somehow, you know, you have to have some, come up with an idea of strategies, yeah, how to.
Yeah.
But in Leonard's, if I understand Leonard correctly, that is still within first order, because you have set out the confines of that set of axioms.
But what would be an example of second order?
I think quantifiers. I mean, we would have to look at some logic book. There's something basic. You take individuals, that's the first order. But once you have quantifiers, you know, like all, and you write those statements in logic, theoretical calculus, then you have properties.
Or inconsistent game, I mean, like axiomatically inconsistent games in some sense, you know, like, you know, game, you know, I would win this game only if I lose this game, or some. If we can make the algorithm bypass this kind of statements, I think then we're probably going to the next order in logic. But I don't know what it means to. It'll be interesting to devise such a game, right? It would be awesome. Like then, you know, it'd go crazy.
But I wondered, you know, people in AI and computer. I mean, I'm thinking about Douglas Hofstadter, who was obsessed with this self-referential stuff, right? He's been doing this for 40 years, right? In Indiana, right? And they have this also because, you know, these people want to understand this crazy hard questions like consciousness and things like that, you know. But they essentially, practically what you see, what they make little models, little games, define little logical games, and maybe they do some, interesting thing like self-referential statements and whatever to see what comes out of that, to get creativity or whatever out of it. I don't know what.
But maybe it's simple. Just maybe modify chess. Like, I don't know, make it one more rule. The king can't check himself, or something self-referential. The king, if the king checks himself, then the opponent wins, or something like that. Or if you want, I just change the rule a bit and then see whether AlphaGo would work. AlphaZero would work. I don't know.
Well, there's this metaphor by Feynman, I think, saying that essentially, the creative work of a theoretical physicist is inventing this game. Essentially, we are working with certain incomplete set of rules, and we are trying, let's say in the standard model, I think, figured out the rules of that chess. Okay, but we don't know what are the rules next. We guess. Maybe there's unification. Maybe there is supersymmetry. Maybe, we go all the way to string theory. But you see, we have extrapolated rules immensely. So we have removed ourselves from the empirical basis.
Yeah.
It's very hard for us to, what people say, falsify, they use these words. I don't know if they're precise words, but, because we have to go from such a high level all the way down. And there's so many things that can happen in between. And there's so many assumptions and all that. It's very precise mathematically. No one says it's not precise mathematically, although it is. But the question is it empirical? I don't know.
This is a moment when you truly appreciate a real face-to-face conference. Because if we were all in the Chern Institute, we go to Boris's hotel room, grab him, and then hear his opinion. You can't do this on Zoom.
But I think, we need to ask him or someone who is an expert mathematical logic, because I would imagine that people doing that, and people, let's say I'm thinking like Gregor Hofstadter, but there's probably other people who was a theoretical physicist. Then he moved to AI in the 70s, right? And then, but he is motivated by this grand question of conscious, whatever, but from a very practical point of view, like logic, physics, physical systems, there are people out there in computer science and artificial intelligence community who have done some of these things. And maybe there are maybe toy models from what Fabian was suggesting. Like, can you prove that, let's say, you need to go beyond the first order logic within some context and blah, blah, blah,
Well, we could ask him. Boris is speaking on the 11th, Wednesday, the 11th.
Okay.
So whoever wants to just stick around.
All right. Great.
Okay.
Fascinating. Thank you, guys.
Thank you guys again. Thank you, everyone.
See you tomorrow. Bye-bye.
Yeah, thanks a lot for putting this together. Yeah.
Thanks, Sven. I wish you would be, you should, next time you would be in person. And we all have beers together.
All right.
Thank you very much for that nice talk.
Yeah, thanks.
Bye.
So